All right, demo number one. The first thing I want to do, I'm showing you right now, this is a wire, okay? The wire right here, the black wire is connected to a power station, which is going to apply a direct current, which means it's going to have current that is flowing in a specific direction, all right? It's not going to be changing directions. Now, the first thing that I want you to do is I want you to look and see, right now, both of my compasses are pointing in the north direction. Okay, straight up that direction. There are no other magnets close by, so they're definitely pointing to the north. Now, I'm going to turn on the power, and watch what happens when I turn on the power. Okay, all right. So when the current starts to go through the wire, you notice that they both, all of a sudden, flip to go over that direction. All right. The first thing this shows us is that moving current creates a magnetic field, right? As the current flows through there, it causes there to be a magnetic field, all right? Now, what we'd like to do is we'd like to try to figure out what direction that magnetic field is. So we can see right here, right, when I turned it on, the reds both turned to flip that way. So above the wire, the magnetic field is going in that direction. So let's go ahead and draw that on. So above the wire, the magnetic field went in that direction, okay? Now, what about below the wire? All right, so I've placed the compasses underneath the wire, all right? Now watch this. When I turn it on, look at that. They're pointing to the right this time. I haven't changed anything else. This is still hooked up exactly the same way that it was, okay? The current, we always talk about current being the positive to the negative. And we talked about this in the last unit, that we understand that it's the electrons that are moving, but we always talk about current as being the opposite. When we talk about conventional current, it's going from positive to negative. So you can see right here, the red is the positive, okay, and the black is the negative. So my current was going from here to here. We noticed that above, it created a magnetic field going that way, and then below, the magnetic field was going the other direction. Now, this introduces us to what we call the right-hand rule. The right-hand rule tells us that when current is flowing, then we can use the right-hand rule to show which direction the magnetic field is. If the current is going this way, then above the wire, the magnetic field is going in that direction. If I curl around beneath the wire, you can see that my fingers are now pointing in that direction, down there. All right, now you could do it with the left-hand rule as well if you wanted to. You could say, okay, left hand, electrons go from the negative to the positive, so they're going this way. So if the current's going that way, above the wire, it's going that way. And then below the wire, when my fingers are below my thumb, then it's going to the right in that direction. So either rule works. When I'm talking about the positive to negative current, I use my right hand. And that's what they use most often in AP. That's why I'm teaching you that one. If I'm showing what direction the electrons are moving, then I can use my left hand, okay? And so that then shows us what direction the magnetic field should be around a wire. Now, let's look at what happens if we have a coil of wires, all right? All right, so this time I have a coil of wires. The wires are spinning around like this. All right, so these wires are going around. So again, here's the positive. So it goes up this way and it goes around this way. All right, now let's see what happens when I start running current through it. So I turn it on. Beep. You see it's going over to the right. Okay, so we're going to change this. That was from our last demo to show that in the middle, the current is going to the right. Okay, now I want you to recognize, again, that was from positive going around this way, like this, and it just kept spiraling around till eventually it went out to the negative. We can, again, use a right-hand rule here. If we're talking about the positive to the negative, that's the direction of our conventional current, we can use our fingers this time to follow the current. So the current goes around this way, and it curves around that way. And if I do that with my fingers, look at what direction my thumb is facing. My thumb is facing the direction of the magnetic field inside of the coil. So the magnetic field goes this way. Now, this is going to work exactly like a bar magnet. It's going to work exactly as if I had, and you'll notice if I had this guy right here, okay, the field will go this way and then out around that direction. And so it's just as if I had placed a north-south magnet there. It goes from the north, and then it's going to come around and go to the south. And so on this side, it's going to go in, and that's exactly what we saw earlier. It was going in this direction. It'll come out and around just like that. And that's what we'll see all the way around that coil there. All right, let's go ahead and have a look at that. Again, we'll turn it on. See, it's going in this direction. Okay, as I bring it out and around, look at that. So it's now curving back in that direction. And as I come over here, it goes back just like the bar magnet. It goes in kind of that cycle, right? That circle. All magnetic fields have to go in a circle. On this side, it would come out, right? It's starting to curve up that way. As I go over here, it's going to start, it's getting a little bit messed up by the power station over there, but you get the idea. The red continues to point in this way till it comes back around in that direction. All right. So that's kind of cool to see how a moving current affects a magnetic field. And so we've seen two different right-hand rules so far. We saw that when the current is going through a wire, that we can use our thumb to resemble the current, and we can use our fingers to show what direction the magnetic field is going. And in fact, we can use that here too. If I'm just looking at this wire, I can say the current's going this way. The magnetic field would be above here. And look at that. When I go below the wire, it says it's going to go that direction, which is exactly the direction we said it would go through the loop. The second right-hand rule we showed was follow the current around the loop, and your thumb shows the direction that the magnetic field should be inside. We did the same thing with our left hand. We said, well, left hand says it goes from negative to positive. So negative to positive would be this way, which says into the middle there. Same thing on all of these. No matter where you put your hand, if you're doing the direction of the negatives, it'll show the magnetic field going into the loop in that direction. Or noticing that the positive was going this way, so the negative has to be going that way around the loop. Okay, and if we do that, if we go around here and we see here goes the negative around that way, notice that we get the magnetic field in the center of the loop pointing in this direction. Okay, so a couple of neat things we're seeing here. One is that the moving electric field creates a magnetic field. All right, and secondly, that we can predict the direction of that magnetic field based off of the direction of the current or the electrons. All right, so here's the last thing I wanted to show you. All right, this is an ammeter. It measures current. Okay, right now you'll notice that it's zero. It's zero because there's no current here, right? There's no battery connected to this. It's not plugged into the wall. An ammeter doesn't have any type of power source. It's only going to measure if there are electrons moving through these wires. Okay, now you'll notice I do have a magnet right here sitting inside. This is just a coil of wires. All right, so the electricity, the circuit goes through here. It goes around and around and around and around and around, and then it comes out the other side. All right, so that's one thing to notice. There's no power here. There's no electricity being created. Therefore, it's zero. Now, watch really carefully what happens to the current as I pull the magnet out. All right, here we go. Did you see it? If you weren't paying close attention, you might have missed it. Here, I'm going to watch when I put it back in. Do you see what's happening? You can see it, but you know what? I'm going to put it up just a little bit. You know, here, let's do this guy. We're going to unclip you here. I want you to see what happens to this guy right here. See if we can get it without the glare. Okay, as we put the magnet in and out. Can you see? Right now I'm putting the magnet in and out. Can you see the little hand? Now I'm not doing anything. Okay, you can see it's not moving anymore. I'm going to place it inside. And it moved a little bit as I placed it inside, but now that it's not moving anymore, it's back on 0 again until I decide to pull it out. And you can see, sorry, I can't hold it and move the magnet at the same time. But hopefully what you're seeing is that as I move it in and out, there's a little bit of current flowing through there. This isn't a super great magnet, but you can see that as long as I'm moving it, that it creates a little bit of current. But as soon as it just sits there, nothing. So what did we learn? Well, we learned in the beginning that moving an electron, moving electrons through the wire, create a magnetic field. And now what we're learning is that moving a magnetic field or changing a magnetic field can create the movement of electrons. All right, so you get both of those. They're tied in together, and this is why we talk about electromagnetism and electromagnetic waves. All right, I got one more thing to show you. All right, so I've got just a bar of metal here, right? And you'll notice that it is not magnetic in any way, shape, or form. It's not picking up those paper clips. All right, not the middle either. So I'm not fooling you here, right? Stay there. I'm not going to take it out of the screen. But what I do have is I'm going to take this wire and I'm going to wind it around there and plug it back in. So this is the same black wire that before was connected up to my power supply. So it's going to create a current that is flowing through the wire. Now remember, if current is flowing through the wire, so look, this is the positive. So the positive is going around here. It's going to go around the outside like that, showing my right-hand rule. And it's going to create a magnetic field going through this bar. Okay. Now, when I do that, power on, you'll notice that, let's get a little bit closer there, that it's just enough to maybe partially pick up. Some of these are better than others. Not quite enough. It doesn't really like it, does it? Oh, there we go. We got one there. All right. So let's turn it off. I'm going to wind it up a little bit more. All right. So I turned it up. Okay. A lot more coils there now. Look at that. Look at them apples. See, it's able to pick up a lot more. More coils means more current going through there. And I'm starting to feel it a little bit warm. More coils mean more current going around, which means a stronger magnetic field, which allows me to pick up even more paper clips. This, my friends, is an electromagnet. That's what electromagnet does, is it takes current, electricity, it runs it around a metal coil, and then when it touches something, see, I just turned the power off. Now it's not working. Turn the switch off, it doesn't work. Turn the switch on, and ooh, I can pick up paper clips. What? Anyway, there you go. So that was the last thing I wanted to show you. Connecting electricity and magnetism through their fields.